Hey everyone, and welcome. Today we're going to talk about something that happens to all of us, food going bad. And we're going to connect the dots from that stale taste of your potato chips all the way to the huge challenge of global food security. So let's dive in. You know the feeling, right? We've all been there. You reach for a snack, you're expecting that perfect crunch, but instead you get this disappointing kind of paint-like flavor. It's a universal feeling, but what's actually going on there on a chemical level? Well, that off taste actually has a scientific name, rancidity. It's the official term for when the fats and oils in our food start to break down and spoil. So it's not just a bad taste, it's a sign that the food is literally decaying. Okay, so let's get right to the heart of it. What's the specific process that turns a perfectly good snack into, well, something you'd rather not eat? The number one bad guy here is a process called lipid oxidation. And it sounds complicated, but in simple terms, it's just what happens when the fats, the lipids, in your food react with oxygen in the air. It's a chemical breakdown that kicks off a whole chain reaction of spoilage. Now here's where it gets really interesting. Kind of ironic, actually. The fats that are the most vulnerable to this process are the very ones we're always told are so good for us, the unsaturated ones, like your omega-3s and 6s. You see, their chemical structure with all these double bonds makes them super reactive with oxygen. And this process doesn't just ruin the taste, it completely tanks their nutritional value. So this whole lipid oxidation thing isn't just one single event. It can happen in a few different ways. Let's meet the three main pathways, the three main culprits that cause our food to spoil. First, you've got auto-oxidation. Think of this one as the slow, silent default process. It doesn't need much to get going, just some oxygen hanging around at room temperature. It's this relentless, kind of self-sustaining reaction. Auto-oxidation pretty much works like a set of dominoes falling over. It all starts with initiation, where a single unstable molecule, called a free radical, shows up. Then comes propagation, and this is the real chain reaction. That radical steals a part from a nearby molecule, which turns it into a radical, and so on and so on. The whole thing only stops at termination when two of these radicals finally bump into each other and cancel each other out. And this diagram here shows that propagation cycle perfectly. You've got a radical molecule reacting with oxygen, which makes it aggressive. It then goes and attacks a stable fat molecule, rips a piece off it, and turns that fat molecule into a brand new radical. And just like that, the cycle begins all over again, spreading that decay right through the food. All right, now for culprit number 2. If auto-oxidation is a slow burn, then photooxidation is a full-on explosion. I mean, look at this. It's activated by light and can be up to 1,500 times faster than auto-oxidation. This is exactly why your olive oil comes in a dark-colored bottle. So how in the world does this happen so fast? Well, as this chart shows, light is the trigger. It hits something called a photosensitizer, like chlorophyll in plants or riboflavin in milk. That molecule soaks up the light energy and passes it to regular oxygen, which transforms it into this supercharged, highly reactive form called singlet oxygen. And this stuff doesn't need a chain reaction. It just attacks fats directly, causing spoilage at lightning speed. And finally, we get to enzymatic oxidation. Now, this one's different. It's not just a random chemical reaction, it's a biological process. You have specific enzymes, like lipoxygenase, which you find in things like raw plants and fish, and they actively target and break down fats. It's just a part of the natural life cycle of the food itself. This table gives us a really great side-by-side look. You can see oxidation is kind of spontaneous and random, a slow, steady process that just happens while stuff sits on a shelf. But enzymatic oxidation is a highly specific, targeted attack kicked off by enzymes in raw foods, and it can be incredibly fast if the conditions are right. Okay, we have gone deep into the chemistry, but now it's time to zoom way out and see how this all connects, from your bag of chips all the way to global security. Because the science of a stale snack has absolutely massive implications for the whole planet. This one little process, lipid oxidation, doesn't just ruin your afternoon snack. It is one of the key drivers behind a much, much bigger problem: global food loss. Just look at this number, 20 to 30%. That's the estimated percentage of fruits and vegetables lost after harvest in a country like Nepal. That is a huge portion of food that's been grown and is ready to eat that just never makes it to a plate. And lipid oxidation is a major reason why. Those very same chemical reactions we talked about are happening on a massive scale between the farm and the store, contributing to this huge amount of food loss all around the world. And a bunch of different factors can create a perfect storm for this kind of spoilage. High temperatures, for example, they speed up all these chemical reactions. Humidity helps mold grow. But maybe most importantly, poor storage and the lack of a refrigerated cold chain mean that food is just left vulnerable to decay for long stretches of time. To really understand the impact here, let's bring this global problem down to a specific place. Let's take a look at the human cost in Nepal. In Nepal, most farms are small and they're rural. They often lack access to things we take for granted, like cold storage. The steep, mountainous terrain makes transporting produce incredibly difficult and slow. It's often carried in traditional bamboo baskets, which can lead to bruising, and that physical damage just makes the produce even more likely to spoil. And the consequences of this are absolutely devastating. For the farmers themselves, this spoilage is a direct hit to their income. For the wider population, it shrinks the amount of food available, and ultimately, it threatens the food security of the entire nation. So, let's bring it all back together. We started with a single molecule of fat reacting with oxygen in a potato chip, and we've ended up right at the heart of the global food crisis. It's a pretty incredible journey from the microscopic to the macroscopic, and it really leaves us with a critical question. We understand the chemistry of why food goes bad, so the challenge now is, can we take that knowledge and use it to design smarter systems, better storage, and more effective policies to build a world with far, far less waste?